So very good morning all. So can you hear my voice? So can anyone tell me please? So if it is audible, so that I can go with my. Okay, Kalyan, fine. So let me share my screen so that we can go with today's class. Okay guys, so can you see the notepad? Can you see the notepad?
Yes, sir.
Sir.
Okay, so fine. So let's start with our today's class. See here, I need more amount of time, so I'm not keep on waiting for the students to come and join. Today we are going to learn about one of the important topic in our unit of dielectrics and capacitance. Okay, so which is known as boundary conditions. Okay. So boundary conditions. So this you can consider it as one of the important concepts. So in our yesterday's class, we have learned about current densities. Okay, so conduction current density as well as convection current density. And now we are going with the next concept of boundary conditions. So before going into the derivation part of the boundary conditions, we will have some idea regarding what do you mean by boundary and why we need to have these boundary conditions. Okay, so derivation part is very easy, just matter of 2 to 3 steps only. But understanding the concept of this boundary condition is very much important, so that you can have you can attempt the answer without any hesitation. Okay. So first of all, we will see what do you mean by boundary. So as I told in our yesterday's class, basic general meaning of a boundary is, suppose if you are having one space. So if you want to have, so suppose you can see this notepad now. So if you want to divide this notepad into two parts, so then what we will do, so we will draw one line. This line will act as the separation line. So suppose if this is region 1, and now this can be called it as what, region 2, and what makes the region 1 and the region 2, this is nothing but what, the boundary line. Okay, so suppose here we know that if we are having two different nations, let it be India. India is our country. Next, our preceding nation is, let it be Pakistan. Okay, so if you want to travel, so from India to Pakistan, so we have some visa process. So let it be, so for Pakistan, maybe visa may not be required. Some of the nations, nations, just with the help of passport, we can travel. But here, suppose let it be a USA or any other country, so definitely we have to have a visa. Why we have to have the visa? Because while crossing the boundary of the country, so definitely we have to fulfill the conditions, or we have to fulfill the rule, we have to accept the rules and regulations of the country that we are traveling. Okay, so that means while crossing the boundary line, we have to fulfill the conditions of the region that we are entering here. So similarly, here also we are having some boundaries. How these boundaries are formed? So that is the important concept. Okay, so as I told in a previous class, so suppose here, since we are dealing with the capacitance or capacitors, we know that for every capacitor there will be one positive plate and one negative plate. For every capacitor there will be one positive plate as well as for one negative plate. So in between these two plates, okay, so in between the positive plate and the negative plate, so there may be n number of dielectric materials, dielectric mediums. So let it be epsilon 1 of dielectric medium, and this is epsilon 2 of one more dielectric medium, and this is one more dielectric medium. Like that, we are having multiple number of dielectric materials of epsilon m. Okay, so here when we give the power supply to the positive plate and to the negative plate of voltage V, so then what is going to be happen? The electrons are going to travel from positive plate to negative plate, from positive plate to the negative plate by crossing these multiple number of layers. So here the positive plate is a conducting material, and here it is a dielectric medium, and here also we are having one more dielectric medium, and here it is also one more dielectric medium, and again it is a conductor. See here, the electron while entering from conductor to dielectric medium, it is crossing one boundary. So this is the boundary between the conducting material as well as the dielectric material. And here while crossing from this dielectric material to the second dielectric medium, here it is crossing one more boundary. And similarly, from one dielectric material to the third dielectric material, again the electron is crossing the third boundary. So finally, it is after finally the dielectric to conducting, while the electron is crossing from dielectric material to the conducting, here it is crossing one more boundary. Therefore, while crossing from one boundary to the another boundary, here it has to fulfill some conditions. We have to fulfill some conditions, and these conditions are nothing but what? Boundary conditions. Okay, so therefore, while designing a capacitor, you have to go with these boundary conditions in order to estimate the final value of the capacitance. The final value of the capacitance. Okay, so with respect to the different boundaries, so these boundary conditions are class. See here the electron is traveling from one dielectric material to another dielectric material. So this type of boundary condition is called as dielectric boundary conditions. This is first step, and second we are having one more boundary. So see here, from conductor to dielectric or vice versa. So conductor to dielectric boundary conditions. And next, the third one, suppose in place of dielectric material, if you are going to treat it as a vacuum, so then we are going to call it, we are going to have as conductor to free space. With respect to free space, we are having the third boundary condition. So these two are very short, but in your essay type answer, so they go with this first condition, that is called as dielectric boundary condition. Before going into the derivation part of dielectric boundary conditions, so first we have to see some of the prerequisites or some of the concepts that I am going to use in order to obtain the conditions for dielectric medium. So what are the conditions that I tell now? Suppose first resolving components. First we will see resolving of components. So that means, suppose if you are having one vector quantity, let it be a, this is one vector. So if you want to resolve this vector, we can resolve with respect to x-axis, as well as we have to resolve with respect to y-axis. So the component with respect to the x-axis is called as x component, and the component with respect to the y-axis is called as y component. How we are going to resolve means, so this vector can be resolved into two components, let it be, that is x component and y component. So the component of x will be in parallel with the x-axis, and the component of y will be in parallel with the y-axis. So this is, let it be, if this is x-axis, and this will be our y-axis, and therefore if you want to resolve the component of a, so this is ax and this is a y, and representing the vector a, so with respect to x component and y component will be, so a will be ax plus ay. So ax plus ay. So these things we will see in case of phasor diagram. So resolving a single component, a vector, into two components, that is ax bar as well as ay bar. So likewise, you can resolve any component, any vector with respect to x-axis as well as y-axis. So here in boundary conditions, okay, so in boundary conditions, so we will take two parameters. So that is electric field intensity, that is called as E, and electric flux density. So these are the two parameters that we will do the analysis for the boundaries. Okay, so we will analyze the how this E is changing, how the D is changing, or what are the conditions this E and D has to be fulfilled. Okay, so now we have to resolve these the vector of E and the vector of D into two components. How we are going to resolve these two? So just as we have done here, we can resolve these two components of A and B, sorry, E and D as, so suppose if this is E, we can resolve this E into two components with respect to X, that is Ex, and with respect to Y, that is Ey. So similarly, we can resolve the value of D into two components, that is dx as well as dy as well as dy. But okay, we will not, I mean, so not but here with respect to this thing, how will be the value of E? What will be the value of E? E is equal to, so Ex plus Ey. So similarly, what will be the value of D? D will be equal to, so dx plus dy. Okay. With respect to that, since we are going with boundary conditions, suppose see here, if this is the boundary, okay, so if this is the boundary, the component which is parallel to the boundary, the component which is parallel to the boundary, we will call it as tangential component. Okay, you have to remember these things. So the component, so which is parallel to the boundary, which is called as what? Tangential component. And the component which is perpendicular to the boundary, the component which is perpendicular to the boundary, we will call it as normal component. We will call it as normal component. We will do some modifications for this resolving of the vector quantity. That is, earlier we have generalized. This is what in general we will resolve with respect to x-axis and with respect to y-axis. But here, since we are going with boundary conditions, we are going to express the resolving of these components with respect to the boundary. Okay, so see here, and now I'm going to draw this vector. Suppose if this is the vector E, and now I am going to resolve this vector into two components. That is, one, this is the first component, and this is the second component of E. Earlier this is what, y, and this is x, and this is x. See, now we have to talk with respect to the boundary, the component which is parallel to the boundary. So this is the, see, observe the x-axis here. The x-axis is in parallel with the boundary. Okay, now we will call this x component as what? Tangential component. And this is the boundary. And with the boundary, so this is perpendicular. The y component, it is perpendicular to the boundary. So now we will call this y component as what? Normal component. So earlier we have written E as what? So Ex plus Ey. But now with respect to the boundary condition, we will write the component of x as what? Tangential component. Therefore, we will represent as suffix t, et, plus now the component of y will be what? Normal component. Earlier it is Ey, but now we will represent as En. So therefore, whatever the value earlier we have written, now these have been transformed with respect to the boundaries. That is what? E will be equal to tangential component plus normal component. So similarly, D can also be written as what? The tangential component plus normal component. Okay. So now we have to derive the conditions for the normal components as well as the tangential components of electric field intensity as well as electric flux density. So see, students, so far I have not derived anything. I am just giving the introduction part and the required things for calculating or for obtaining the boundary conditions. So this is all the basic foundation for obtaining what? The boundary conditions for any type of condition, that is for dielectric as well as conductor dielectric as well as for free space. So for in order to get the conditions for any type of these three, so definitely we have to understand all these concepts. Okay, so first we are seeing how to resolve one component. So we have resolved the component into two, that is with respect to x and y. But here, since we are going with respect to the boundaries, so whatever the component of x, so whatever the component which is in parallel with the boundary, we are going to call it as a tangential component. Whatever the component which is in perpendicular to the boundary, we are going to call it as a normal component. And whatever earlier conditions that whatever the earlier resolving components we have got, so we have derived them with respect to the boundary, or we have changed them with respect to the boundary. That is, E is equal to Et plus En, and as well as D is equal to Dt plus Dm. So this is the first one. First things that we have to understand. And next, I'm going to use the equation, the required equations for E and T. But before going to show, before going to write those equations, what are those equations that I'm going to use to obtain the boundary conditions? I'm going to recollect some things that we have already learned earlier. So that is potential or electric potential. So this equation that we have already derived, so that is VAB is equal to minus of A minus integral of A to B of E dot dl. So this is the equation that we have already derived for electric potential. See here, so suppose if you are having one wire of having two ends, so this is A and B, and now if you are having the potential at A as VA and potential at B as VB, so what is the potential difference between these 2 points? The value will be VAB. But if you close this line, that means you are doing short circuit. If you are having a wire, suppose if you are having a wire and you are closing it, then what you will call it as a short circuit. What is the voltage for a short circuited line? That value will be what? 0. So therefore, in order to get the boundary condition, here we will take one closed loop. Okay, so we are going to take one closed loop. Since we are applying the electric potential for this closed loop, whatever the value of VAB, that value will be equal to 0. So therefore, what is the condition here? VAB, earlier it is minus integral from A to B, that is E dot dl. If it is closed, then we have to write it as the closed line integral. That value will become equal to 0. So that implies I can remove this negative sign. So closed line integral of E of dl will be equal to 0. So this is the required equation, the first required equation to have the boundary condition. So how this value is becoming 0? So only when that line is closed. So what? So you can write it as closed line integral of E of dl is equal to 0 when, so if and only if line is closed. So whenever, so if and only if the line is closed, then only you can have the voltage as 0. So otherwise you cannot write this value as 0. Okay, so this is our first required equation in order to analyze what the electric field intensity. Electric field intensity, it is nothing but what? E. So in order to get the conditions for E, I will make use of this equation. Next, what is the second equation we required? So we required D. So D is nothing but what? Electric flux density. Electric, so flux density. So for the purpose of electric flux density, okay, so we have, I will make use of flux condition, that is D is equal to, so d psi by ds. So d is equal to d psi by ds. So what is basic definition? I'm making use of basic definition. D is equal to what? Total flux divided by unit surface area. So therefore D is equal to d psi by ds. So that implies what will be the value of d psi? So d psi is equal to d ds, and if you integrate on both sides, psi is equal to integral of d ds. Now if you want to apply Gauss law, so then whatever the surface that should be enclosed. What is Gauss law? So Gauss law is nothing but psi is equal to q enclosed. So whatever the surface that here you have considered, so that should be a closed one. So then I can apply the Gauss law here, so that whatever the value of psi is there, here I can write it as q enclosed, and this value will be equal to d of ds, but this surface should be closed, so therefore you have to do closed surface integral. So this is the second equation that I am using. So this is not the new thing. The second equation, whatever the the calculation part that I have done for second equation, this is not new for us. This is the thing already we have gone under applications of Gauss law. If you remember, under applications of Gauss law, so this is the common part that we have done for every application. Just what I am doing recollecting. That's why I told I am recollecting few things of electric potential as well as electric flux density. So from that recollecting, I have derived one equation. The first one, that is nothing but closed line integral of E dot dl is equal to 0. And again the second one, that is closed Q enclosed is equal to, so closed surface integral of d ds. So I am making use of these two equations in order to have the boundary conditions. Okay, so now I am summarizing. So summarizing the things, the required things. Okay, the required concepts for boundary conditions. So that is the first one, resolving part. So that is with respect to boundary. So we are resolving what E and D with respect to boundary. The components with respect to boundary, we are having tangential and normal. So therefore we have resolved the first part, that is E will be Et plus of En, as well as D will be dt plus of dn. Okay, so second, we have gone with the analysis part of D and E in order to have the required conditions for D and E. So we will make use of two equations. The first equation for E as, so closed line integral of E of dl is equal to 0. And for the second one, so Q enclosed is equal to closed surface integral of d of ds. Okay, so these are the prerequisites concepts to obtain the boundary conditions for dielectric conductor, as well as for free space. Okay, so this is all the things. And now we are going with the very first one, that is what? Dielectric boundary condition. So in your examination, you don't require to write all these things, but you have to write a few points, whatever the summary here I have written. Okay, so you have to write that summary before going into the boundary conditions of dielectric. So first you have to keep the heading as boundary conditions. Okay, so first you have to write the heading as boundary conditions, and for the first one you have to write the resolving part, and later the second point you have to write what the required equations for boundary conditions. Don't worry, so we will have that xerox of that notes, and with that note you will get idea how to write the exam. Okay, so don't worry about that. So first is dielectric boundary condition. So as I told that here we are having one boundary here. So I have taken one boundary. So this, why I have called this as a boundary means, so here we are having one dielectric medium, whose constant is given as epsilon 1, and here you are having one more dielectric medium, so whose epsilon is given as epsilon 2. So therefore, what makes the separation between electric medium epsilon 1 and epsilon 2? This is nothing but what? Boundary. So this is the boundary. So now, when the electron is traveling from one boundary, from this boundary, this dielectric medium, and crossing the boundary, and if it is entering into this, the second dielectric medium, okay, so now we have to do the analysis part. So electron, obviously, because of that electron, it is having the electric field, and by making use of these two parameters, that is E and D, for both in both mediums, okay, so we will finally derive the condition. So with the conditions, we will make some conclusions, and with that conclusions, you can have the idea. See here, now we can resolve the vector of E. So first we will go with the calculation for E, later we go for D. Okay, so for that I am arising now whatever the components I am going to resolve, that thing I am going to write it here. So first I will go with E. With respect to dielectric medium of epsilon 1, it is E1. With respect to dielectric material of epsilon 2, this is E2. Now I have to resolve the value of E1 and E2 with respect to boundary. So now I am resolving. So see here, earlier we have resolved like this. So E, so tangential component and normal component. Tangential component and normal component. So therefore, see here, in some textbooks, we will have another diagram that I will tell right now. So here, this is E, and resolve this E with respect to ET, and resolve same with respect, and resolve the same with respect to EM. And the same thing we can write as this is EN, because these two lines are in parallel, and this is also ET, because this is also in parallel with ET. So that means, suppose if you draw one triangle, a square box, if you are having one square box, and this diagonal will act as what? The vector. If E, whatever the normal components are there, so this is En, as well as this is also En. Whatever the tangential components are there, that is nothing but the parallel lines are there, this can be treated as Et as well as Et. So in some textbooks, okay, so in some textbooks they will draw this triangle, just wait. In some textbooks they will draw this triangle. In some textbooks they will draw the lower triangle. Okay, so both are correct. You can go with this triangle or you can go with this triangle. Okay, So for our simplicity, I will make use of the lower triangle to draw the tangential component as well as the normal component. Okay, so first I will draw the tangential component. Tangential component should be now, I mean, in parallel to the boundary. So therefore, here I am drawing this is called as tangential component of E1 as well as E2. Next, I am going with the normal component. Just wait. So I am going with the normal component. So drawing perpendicular line to the boundary. I have drawn perpendicular line to the boundary. So this is normal component, and as well as this is normal component. So normal component of E1, that value will be E1 with respect to suffix n. Normal component of E2, that will be E2 suffix n. So similarly, tangential component of E1 will be E1 suffix t. Tangential component of E2 will be E2 suffix t. So E2 suffix t. E2 suffix t. Okay, so this is the way how to draw the tangential components and normal components for electric field intensity of in different dielectric mediums of epsilon1 as well as epsilon2. Now, in order to apply this equation, I'm going to take one closed loop. Okay, so see the arrangement of this closed loop, how this closed loop will be. I'm going to take that closed loop. That closed loop will be half in one dielectric medium and remaining half will be in another dielectric medium, so that I can have the behavior of electron inside this loop in two different dielectric mediums. Okay, so let it be, since I am going to call it as a loop, I am writing it as A, B, C, D, and it is a closed loop, so that if it is a closed, obviously we have to give one the direction. This closed loop is having a width of delta W, and it is having a height of delta H, so that half of the loop is delta H by 2. It is present in dielectric epsilon1, epsilon2. Remaining half is available in second dielectric material, that is delta H by 2. Delta H by 2. Okay. So this is the schematic diagram for analyzing electric field intensity, capital E, in two different dielectric mediums. So that is the reason why I have taken half part of closed loop in one dielectric material and remaining half part of loop in second dielectric medium. Okay, so since we have to analyze in both the dielectric medium at a time, okay, so that is the reason why I have taken this dielectric this closed loop half in one medium and remaining half part in second medium. Okay, so this is about the diagram. I hope the time is running out. Okay, so in next class I will go with I will draw the diagram directly. Okay, and we will proceed with the derivation part.